How do we hide this? Okay, so hello everyone again. I'm Alex, and I will administer the reproducibility challenge for this year's student cluster competition. So first of all, I'm not going to show slides. I will go over tabs and some code to show you quickly how you can run some stuff. But I have some notes in a slide in Google Slides. So there is going to be a discourse channel that maybe you don't have access yet, but you will have soon. And I made a post here, notes from the webinar, and there is a link here, and you can see the notes over here. So you can go over them. So I see some of you are already there, and copy paste some stuff that we are going to discuss. Okay, first of all, what is the reproducibility challenge about? So last year we had a paper that was about Python. So the reason it's about Python is because it's a very popular language in the scientific community, because it has a lot of tools and allows the domain scientists to be productive. It's easy to write a scientific code and make experiments. But the problem is that Python is many times not fast, especially if you're writing a high-performance computing application. And the idea is that we want to find a way to make Python fast. So there are two aspects to this. First of all, there is that we have made in the past a benchmark about Python centered around using the NumPy module to write scientific applications. And we also have a framework that can get in the front end a code that is written in Python or a subset of Python, and then it can optimize it. So I'm not going to spend more time in the webinar to discuss about the work, because you can find everything online. So there is also the link to this web page, and you can find the paper on archive. You can also find it in the ACM library. Some slides, as also a video on YouTube of the presentation. So let's continue now. So the main things that you have to do for this challenge is that you will have to recreate some results. Let me show you more specifically. So I will just go to the paper on archive. And what we are going to center around is the performance of, let's say, the reference version, which is with the CPython interpreted of the benchmarks on CPU, and also with our framework, the DAIS framework, also on the CPU. So for this, you will see that there are two main figures that we are going to focus. So it's figure 7, and we are going to be asked to run basically the reference version and also the DAIS version, and then make a comparison and see how this looked compared to last year's paper. And the other results we're going to do are distributed, but also only on CPU, and this is figure 12. So we will not have other frameworks like Dask or Ligate. It will only be DAIS, and then you will check how well it scales. So here we run weak scaling results, weak scaling experiments. So how you can run this, you have to get two main pieces of code. One is DAIS and the other is NPBench. So I will start with DAIS, so you can find it in GitHub and you can clone it. And then you can install it. So let me, since I have this now open here, let me go a bit on my slides. So there are a number of submodules, so don't forget when you clone to do this recursively. So I'm suggesting that you actually don't download a specific release yet with pip, but you actually use the GitHub repo, because we have made a number of changes and we will freeze it eventually for the competition. So you have to clone it either recursively, or after cloning you have to do submodule update. You should know that we support versions 3.7 to 3.10. I think 3.10 is the latest that it's out now, and this is what I have been testing also lately to see what you're going to run. And you may want to use a Python virtual environment, because maybe you have other projects and you don't want to make a mess. And also for performance reasons, you should have in your system a BLAS library. So if you're on an Intel system, this will be MKL, but on another system, OpenBLAS will work fine. Now, I suggest that you install in development mode. For example, for some of the tests that I will show you today, I made a branch because I updated the scripts to make some tests easier. So you have to install it like this, basically. And if you want to run some tests, this is not for the competition, but it's if you want to play with the framework, then there are some extra module requirements, and you can install it with this line. And after you do this, you just have to run some simple examples to verify the installation. So I will just show you here how this works because I have it open. So and this will run something. You can see what this is in here, and if you're interested, you can play with the framework and also ask us questions, both on the resources that will be available to the teams, but also on GitHub. Now, of course, if you have any installation issues, there is documentation that is in this link in general. So there is a particular branch, not the latest ones that you might see down here. Here we have more detailed documentation, and we have installation instructions and troubleshooting. So if when you try to install, you have any issues, you can have first a look if you can find the solution to your problem here. Otherwise, you can always, of course, use the competition resources or GitHub to seek assistance from the development team. Now, the next piece of software that you will need is NPBench. So this is also on GitHub. So this is the address here. It's also on the slides. So you will have to clone this, and then you will have to install some requirements, and then you can run some benchmarks. So I will show you actually how you can. Is there a question? No. So I just have this here. So now how you can run benchmarks. Here we have a few scripts. So we have the script run framework and run benchmark. So what does this do exactly is the run framework will just run all the benchmarks that exist in NPBench. So you really want this, for example, for figure 1. Or was it 7, sorry, for a particular framework. So you will need to run this for NumPy and ACE. So for NumPy, you will do -F, which stands for framework, and write NumPy. And then we have some dataset presets, and you want to reproduce the results from the paper. So you're going to have to run paper here. And when you run this, then you will start seeing something like that. So what this does, it goes over all the benchmarks one by one, and it runs one execution to check whether the results validate, and then it runs multiple times and reports the median. Now, all the results are being recorded in a SQLite database that I will show you afterwards, and from there you can make some kind of plot. Now, if you want to run it for days, you will just change instead of NumPy and use days CPU. When you run for days CPU, you will see that there will be 3 different executions, so it's not a single one. These are for 3 different optimizations workflow that we have, and basically the best will be chosen. And it is possible that some fail or they don't validate, but you don't have to care about this. Now, after you finish executing those, then you can also get invocation results. I'm not sure if it will work now because I'm on SSH, but let me give it a try. Python, what is the plot results? And so there is this plot results script that can read this database that has been written. You also have to give the preset because it will filter by preset the results, and it will create a PDF and also show visualization. Now, I'm not sure if I can, let's see what's going on here. Yeah, unfortunately, I was intending to show that. So this is this heat map, but I will try to show you at the end how it looks. So this is one part. And let me see now exactly what I wanted to say here. Yes, another thing. So to get the better results, or you will also read in the paper, you may want to limit the number of OpenMP threads. So what we did for our testing in the paper and what we generally suggest, because we see you get the best results, is to limit them to the number of physical cores. I mean, this is especially common if you have an Intel CPU and it has hyperthreading. So you can do this by setting the environmental variable before your command line, or I also said how you can set this in a more automatic way if you prefer. Now, the other part of the testing is the distributed results. So here you will need a few extra elements. So first of all, you need to have an MPI library installed. So we suggest MPI-CH because this is what we have used mostly, but also OpenMPI should work in principle. And a number of the tests that you will have to run needs Scalapack. So this can be MPL if you're Intel, but also reference version or a self-compiled one should work. And finally, you will also need to install the Python module MPI for Pi. So you have to do this after you have installed MPI. Now, this is why I made a number of differences. So what I'm going to tell you to work with is this branch update -p library, because last year we only worked with Intel MPL on Cray MPI, which is based on MPI-CH. But this year you will probably have different architectures and may not have Intel or MPI-CH, but OpenMPI. So we have made some changes to support generic Scalapack, and I just want to show some issues that you might have, and you may need to edit some files for the environment. Of course, I will just show some stuff here, but if you have any issues, you can always contact us to help you with that. So if you go inside this, there is a folder libraries, and here you have different libraries that we have. So the important thing is the MPI library, and we have environments, and then we basically use CMake in order to find the MPI library and the header files and include them all appropriately. So for MPI, I don't think that you will have an issue and this should work. If there are any issues, let us know. The problem that will happen might be with Scalapack. So here you can see that I have 4 different environments, and I will also show you how you can select them. And for example, for MPL, we have made here a file that should hopefully link everything properly. The main issue happens because MPL, especially if you want Scalapack, you need a custom linking line that we kind of generate here. But what is very likely to happen is that at the end, you also need to tell the linker, okay, where is my MPI library in this linking line? And unfortunately, with the infrastructure that we have, we cannot have CMake do this automatically. So, for example, in my case, what I have done, I basically, if I'm on my desktop machines where I have MPI-CH and it's on my library paths, I just add here at the end -l MPI-CH. But for example, when I want to run, we run the test on the Pittsdyne supercomputer, and then I need some other library. I made an environmental variable that I pass, and then I set exactly what I want here. So maybe depending on the machine that you have with, maybe you will have to do something, or maybe you will not, because everything is in the path, and the linker will find them. But if you have any issue, you can try to edit these files. Now, I have tested all of this. So we have MPL, MPICH, we have for OpenMPI. Unfortunately, I do not suggest using this because it crashes for parallel gem, and I don't know why. So I've been able to make it work. So for Scalapack, we use pgem and pgemv. This environment links and works with pgemv, but not with pgem. I would suggest that you don't use. If you are on an Intel machine and you want to use MPL, use either MPICH or Intel MPI, which should use the same basically link line. Now, if you're not on an Intel machine, then you probably want the reference Scalapack or compile it yourself. So to test this on an Ubuntu, I just installed the Debian packages for Scalapack for MPICH and for OpenMPI, and I tested those. If you can use those, this is fine. If you install your own, you might want here to edit, okay, what is exactly the name of your library? And you want to put in the library paths where these SO files exist. These packages do not come with a header file. Now, if you compile a reference Scalapack, I suppose this will also generate a header file, but you don't need this. I have already created a header file with exactly the functions that you will need. So this is here, and you will not need to do hopefully anything else. So this will probably be the hardest part, that you might have some technical issues to make this work. Otherwise, this is pretty straightforward. So for the distributed test, I have made a new script file that should work well. So I have already also tested it again on Pitstein. So this file is, you will find it here to show you. It's samples distributed, and there is this Postman's files. So this will run exactly all the tests that are from figure 11 in the paper. And this one takes only a particular input. Here, if you want, it has an optional validate flag. Let me actually show you a bit how you can use this. Quickly. Okay, let's see, we're a bit lucky. So I'll try to actually run, but I just want to show you the command line. So what you want to do is, just start here, let's see, 34. So if you run it like this, for example, now we'll run it on a single MPI process. Oops. This will run the script. So how the script works, we do weak scaling. So there are some initial sizes, and it will automatically compute the scaling for the number of nodes and generate the programs and run everything. Now, what you can do, if this is a bit slow, you can also add a flag at the end. This will take a while. what we will do is that if you're on a single node and you want to test that this works, you can try to run with multiple processes. I don't know how many cores you have on your machine, let's say 2, 4, 8. And if you enable the validation flag, what this will do is that it will automatically reduce to a much smaller data set that can actually fit on a single machine, and it will still run this distributed over the MPI processes, but then it will also run the test on a single MPI process and then do validation basically. So this will give you some results. Okay, this will take a while to run. Let me see what else I wanted to show you. And yes. So something more. In this, there will be a configuration file basically. So I can try to open this. You can edit this in order to change some options. If you want to see what options exist, you can go into this. There is this configuration schema, and it has all the configurations flags that we have and what are the default values. What interesting you here are the following. So let me find this. So there is a category that has to do with the compiler. So here you can change what are the library prefix and extensions. So I don't think you will need this because we already have default for Linux, and I suppose most of you are on Linux. If this is not the case and you have any issues, please let us know. Here you can change the build type. The default is release with debug info. Maybe you want to change it for release. And of course, then it's also the actual compiler that will be used. Here we are, so for the CPU. Now, by default, this is empty. And if it's empty, it means that it will try to use the GNU compiler. Now, if you have another compiler on your system, I still suggest to use GNU, but otherwise you can change this here. So if you go to the configuration, so this will be on your home folder, .days.conf, then you can basically put compiler, CPU, executable, and then put something else. So C++ is basically the default that will run, but I don't know if you have Clang, you can set this here. And if there are issues with the compiler, you cannot change this again, please let us know and to find what we have to do. Another thing that might matter, if especially you change the compilers, is the compiler flags that you're going to pass. So these are again set for GNU, the default, and we also have some default for Windows. I don't think anyone will run on Windows, but for example, if you do not have GNU compiler, but you have Clang or something, then maybe you need to change the compiler flags. Finally, another set that we have is about the libraries and what are the default implementations. So for all the tests that you will run, there is an auto-optimization workflow that we run that will try to select an optimized BLAST library, for example, from your machine. But for some workflows, this is not necessary. So if you have optimized BLAST lab, you have MTL or OpenBLAST, you can set this here. So this will be library BLAST if an implementation. So I have put OMKL, but this will also work with OpenBLAST, assuming that this is installed and it is in your system paths and CMake can find it. And the important thing here for the distributed test is also the PBLAST library, and then you can select here what you want. So what we have basically available is MTL MPICH, and then we have also reference MPICH and reference OpenMPI. So these three options, there is also MTL OpenMPI, but I didn't make it work well. So if someone tries and you have a result, please let us know. The rest here, this you don't need to care about this because this is handled automatically by the testing script. Now, there is of course also the artifact. So I also have the link here so you can find it. We will not have you, so this is also linking to older versions of the framework that run the test from last year. For the competition, you will not run these versions. We want you to run the newer versions. But there are a lot of scripts here that help you create graphs or maybe run some tests. So you are free to take whatever you want from there, use it for whatever task we will ask you to do for the competition. Like for example, if you go to distributed, then you can see here that we have this plot function that can get some CSV files that we produced last year, and actually the CSV files with the script that I show you is exactly the same. The only thing that I changed is instead of sockets, it says processes. You can reuse those and adapt them to make some plots that we will ask you to do. So that's it more or less for my main presentation, and we can proceed with the Q&A session. Let me see if there are any questions.
Thanks, Alex, for the great demo.
Hi, I have a question on the competition.
Yes.
So, like, are there any requirements that we should write in our paper for us to get a high score for the reproducibility challenge?
Okay, so we have not decided yet completely what you will have to do. So in a few weeks, we'll come back with something more concrete. What I can tell you for now is the following. So definitely there will be a very pure reproducibility part. So definitely you will have to run the single node CPU benchmarks and the distributed CPU benchmarks. And I think this has to be happened. You will have to make a report where what did you do? What did you find? What was different from last year? Why you think this was this? And we will probably have some questions. And so you will be graded on completeness and quality of the answers. And we may also have some extra tasks, but we have not decided yet on this. So I don't want to tell you something and then you start going on an expedition somewhere if this is not yet clear. But basically, yes, the main thing will be you will be given tasks to, okay, run please these tests and report on them. And of course, you can also try to see, okay, how many iterations you have to run this to get a statistically significant result and all that kind of stuff. Does this answer your question?
Yes, and I have another question, not really related to the challenge, but related to the paper. So I read through your paper and the video. You talked about like how many times you are better than the rest of the programs we compiled. Are there any weaknesses of this DAS program? Because it seems that everything we talked about are the advantages.
Well, of course, there are various weaknesses. The first weakness is that this cannot parse all of Python. So this works with a specific subset of Python. So for example, we cannot work with lists, tuples, dictionaries as data. So this can be used in, for example, in some NumPy methods that we understand. When you want to decide the accesses, then there you can put a list or a tuple and specify what you want to reduce, for example. But if you have data in a list or a dictionary, we do not support this. What we support as data is basically an interface to NumPy arrays. So there are programs that you may have to rewrite significantly in order to take advantage of this. Or, for example, yeah, actually, we now have some kind of understanding of classes and some methods, but it's not that everything works. It's a subset that we can understand and analyze, and then we parse this to R in the mid representation, and then we can compile it. So yeah, the obvious disadvantage is it's not the whole of Python. It's a subset of it, and it might depend on your application. If it's like highly let's say linear algebra and other mathematical formulas, that this can be very straightforward to port, or it might need more work, basically. Other than that, I wouldn't say that we don't understand, we cannot work with recursion. So if you have recursive algorithm, this is not supported. And there are no plans at the moment to make this work. But other than that, this will eventually generate C, C++ code with some optimizations. So it will be written with more optimizations compared to if you wrote the original Python program straightforward to C. And then, of course, there is also what the compiler will do.
Thank you so much.
Yeah, you're welcome.
There is a question on chat.
No, so you will only run the reference execution, which we call NumPy. I mean, it's basically the CPython interpreter, but this is just using the NumPy module and the Days framework. You will not run any of the others, or at least there are no plans to ask this at this point.
Any more questions? If not, thank you so much, Alex.
You're welcome, and please try to run some of the things that I show you today and come back to us with any issues that you have, so we can iron out all these issues a few weeks before the competition, and then you can work with it.
Steve, do you want to say a couple of words about what the best communication methods are if the students have questions going forward?
Sure. So in a few days, we'll send out an announcement and invites to the discourse channel that Alex mentioned. And the purpose of that will be for Q&A about the competition generally, but especially about the apps. So the app experts will be on it and answering questions. And you can also show off your knowledge and help each other out by asking and answering questions as well. So that will be announced sort of in the next week, I'm hoping. And yeah, I think that's going to be the best channel for asking questions. So that.
Yep, we definitely strongly recommend that you use the Discourse channel to ask questions and share feedback, so that everybody, all the student teams will be in the loop and will be aware of both the questions and the answers. And yeah, that'll work out best for everybody. All right, thank you again, Alex. I guess we can wrap it up.
Sounds good. Thanks again, Alex and Abhinav.